Let's talk a little bit now about the thrust, the friction force, and the drag. Okay, so we've already derived the acceleration distance, which is a portion of the total ground roll on takeoff. So just as a review, the acceleration, well, we've derived an equation that can be used to find the acceleration distance, I should say. So in order to find the acceleration distance, we can use this equation, si plus 1 minus si equals the integral of vi to vi plus 1 times w over g, so w over g times the integral from vi to vi plus 1 of v minus v headwind, v sub hw, divided by t minus d minus fr dv. Okay, and so what we said is that in order to find the acceleration distance, we take this equation and we're going to apply it over an interval or a series of discrete intervals. Okay, so if we have some distance like this, we're going to apply this equation over a series of discrete distance intervals. And the reason for that is to approximate any nonlinear or to approximate any general changes in velocity or force. Okay, so that we can evaluate this integral. And in general, this integral would have to be evaluated numerically. But there are some cases in which we can apply this integral a little bit more easily. And I'm going to talk about how that works right now. So making some reasonable assumptions, we can simplify this so that we don't have to integrate it using a lot of difficult numerical methods, or so that it comes out a lot more cleanly. So in order to do that, we need to take a look at this term here on the bottom, or these three terms, I should say. So we're going to talk about each of these individually. And we're going to talk about thrust first, then the friction force, then the drag. Okay, so let's start with thrust. I'm going to do thrust in red. Okay, so the thrust is a function of the power plant. We've talked a little bit about this before. And so it really depends on what power plant we have. So to illustrate this, let me consider three different power plants, and I'm just going to do this kind of graphically to give you an idea of what's going on. Nothing here is going to be all that precise, but it will give you an idea of what I mean when I say that the thrust depends on the power plant. So here we have three plots, each with airspeed on the x-axis, and on the y-axis we're going to have the thrust. Okay, and so the first power plant that we'll consider is a turbojet. So turbojet engines generally have constant thrust as a function of airspeed, or nearly constant thrust as a function of airspeed. Okay, so the plot would look something like this. On the second plot, we're going to have a piston engine with a constant pitch propeller. So this is like your typical general aviation piston propeller combo here. For this type of power plant, the thrust as a function of the thrust decreases almost linearly with increasing velocity. So it looks something like this. Now, of course, these are not to scale. Turbojet would produce much more thrust than a piston and propeller combo. But you get the idea here. The trends are what matter. And then finally, let's consider a turbofan engine. Now, in a turbofan engine, the thrust increases parabolically or very nearly parabolically as a function of airspeed. Okay, so we have these three different things. Now, here we're going to mostly consider this case where the thrust increases nearly parabolically. And really, for most aircraft, we can use a parabolic approximation over each small interval here to get a piecewise parabolic function of airspeed. So, we could break this up into small parabolic chunks, and we could break this up also into small parabolic chunks. So in a very general sense, for most power plants, we're going to approximate thrust as a parabola. So T, well, I won't write this out, but you get the idea. So in other words, what we'd have then is the thrust is going to equal some T naught coefficient. So we're going to give a subscript I because we're, saying that this is for a small discretized chunk here. So T naught I plus what we're going to call T prime sub I times velocity plus what we'll call T double prime sub I times velocity squared, where each of these coefficients, T naught, T prime, and T double prime, are determined by experiment. So let me just write that there. Okay, so they're determined by experiment. Okay, so this is the approximation for thrust that we are going to use most. Okay, you have this parabolic approximation. Now let's talk a little bit about the friction force. So I'm going to scroll down, remind you of the thrust here. Let's pull up blue. So friction force. Okay, so if you'll recall your last lesson about friction, you'll recall that force of friction is equal to some friction coefficient, which for this case we're going to call mu r, which is our rolling friction coefficient, or coefficient of rolling friction. So it's that coefficient times the normal force. Now, on our aircraft, the normal force is going to be the weight minus the lift. Okay, so if you recall, we have our aircraft. I'm going to try and draw this fast, so it's going to look really ugly. We have weight straight down and lift straight up. So our normal force on the ground is going to be the lift minus the weight. Okay? So here's our friction force. Now, we know what the lift is. We can rewrite the lift in terms of the lift coefficient because when we're in our acceleration phase, the aircraft attitude is constant. The angle of attack is constant. Okay, so we're rolling along. The aircraft is not changing the angle of attack. All three wheels are staying on the ground, and so the angle of attack and by extension the lift coefficient are determined based on the landing gear. Okay, so because our lift coefficient is constant, we can write the lift then as mu r w minus 1/2 rho v squared SW CL, where CL is constant. Now our velocity, of course, is not constant. We're changing velocity. Okay, now so just a note about our coefficient of rolling friction. The coefficient of rolling friction generally ranges from about 0.01 for like a nice paved surface to 0.04. Usually ranges from about 0.04 for a nice smooth surface to 0.1 for like a grass landing field. And it could be even higher if you have like loose gravel or dirt. And when we talk later about brakes, we're gonna apply brakes essentially by increasing the coefficient of rolling friction. Okay, so that's just kind of a quick side note. Okay, so now we have an expression for the friction force, which I'm going to square here. Okay, so that's equal to f sub r. Okay, now finally let's talk about the drag. And I've left this for last because there's something special that happens here. So I'm going to go straight to green. We're going to talk about drag. So we know how to write the drag coefficient, or how to write drag from the drag coefficient by now. So drag is just simply 1/2 rho v squared SW times CD. And we also know that CD is nearly parabolic in CL. But there's something special that happens when we're really close to the ground. So our drag coefficient, as it starts out like we'd expect, CD naught plus CD naught L times CL. And then we're also going to have our CL squared term, pi ERA. But there's this term here, there's an extra term that shows up when we're close to the ground. And it's going to look like this, 16 HW divided by pi BW squared divided by 1 plus 16 HW divided by pi BW squared. Okay, so this term here, you may or may not be familiar with it. This term comes from ground effect. And here, this HW is the height of the wing above the ground. So let me just draw something real quick here. We have our aircraft. This is, again, not the prettiest picture. You get the idea. And here we have the ground. So this right here is this distance here. Sorry, I shouldn't draw squiggly for that. It's a little confusing. So this distance here is HW. It's the height of the wing above the ground. And then, of course, BW is the span of the wing. Sorry, that is the semi-span. We should make it a full span. There we go, BW. Okay. So you'll notice that as we get closer and closer to the ground, this term increases. And so excuse me, let me rephrase that. Okay, as we get closer and closer to the ground, this term approaches 1. As we get farther and farther away from the ground, excuse me, I keep saying this wrong. As we get closer and closer to the ground, this term becomes smaller, okay, because we have this 1 plus on the bottom. So if HW gets really, really small, we're going to have 1 plus a very small thing on the bottom. And, okay, let me try this again. I apologize. What really matters here is the ratio of HW to BW. Okay, so if your height above the ground, if the ratio of your height above the ground to wingspan is less than 1, then squaring this term is going to make it really small, and then we'll have a really small term divided by 1 plus a really small term on the bottom. And so what we get then is, as this gets smaller and smaller, as this ratio gets smaller and smaller, as we get closer and closer to the ground, this term gets smaller and smaller, and so our induced drag gets smaller and smaller. As we get farther and farther away, HW over BW increases to above 1, then this term approaches 1. Okay. Now this expression here was taken from McCormick, which you may be familiar with. McCormick wrote a pretty popular book on aerodynamics. And in his early editions, this term had a typographical error where the pi was not included in the denominator of these terms here. In later editions of the book, that was fixed, but you'll see in some other books, people have propagated the error of missing the pi. So it's very important to remember that. Now, McCormick is one of many who have given an approximation for ground effect. And this approximation isn't necessarily the best, but it does the job for what we're trying to show because it shows us this trend. Now the reason that ground effect happens is because if you'll recall, if we have an aircraft flying in the air here, we have these wingtip vortices that are generated because we have regions of low pressure underneath the wing. Excuse me, we have high pressure underneath the wing and low pressure above the wing. And so the air wants to come up to the top of the wing from high pressure to low pressure, and so it generates these wingtip vortices. And this is the mechanism by which downwash is produced, which tends to decrease our lift coefficient and increase our drag coefficient, our induced drag coefficient. In fact, that's the mechanism by which induced drag happens. Now, if we get really close to the ground, draw this airplane again now close to the ground, similar to what we have above. Okay, so when we get close to the ground, these wingtip vortices are they interfere. The ground interferes with them, and so what happens is we get less downwash, and in fact we end up getting more lift than we would have away from the ground, and less induced drag because we don't have the downwash that's inducing the drag. All right, we don't have as much downwash, I should say. And so pilots will often talk about kind of this feeling of like hitting an air cushion when they get close to the ground, and that's because as you get close to the ground, our lift will increase and their drag will decrease, and it kind of feels like a cushion. Okay, so it's important to consider this when we're talking about takeoff and landing. So what we can see from our expressions of drag, friction, and thrust, I'm going to try and get them all on the same page here. Let me just square the drag just to keep things consistent. Okay, the real key takeaway here is you'll notice we have, I'm going to go back to white for this, everything is a function of v and v squared. Okay, we have a parabolic function here. Everything that we have here. Again, the lift coefficient here is constant, and so that reduces to a function of velocity. Okay. So if we come down here, what we can do then is we can take our equation for the for the distance traveled in an interval, and we can rewrite it as something like this. So we have v minus vhw divided by some coefficient plus some coefficient times v plus some coefficient times v squared divided by dv, where these coefficients come from taking, pardon me, zoom in there. They come from taking thrust minus the friction force minus the drag. Okay, and we combine terms, and then we come out with a term plus a term times velocity plus a term times velocity squared. I hope you can see how that happens. Okay, and when we do that, then that gives us something that's a little bit nicer than what we had before, and we can really easily integrate this and sum up our delta S here over our different intervals to get our acceleration distance. Okay, now we can also extend this. Okay, so this is for a small time interval, but actually we can generally get a decent approximation by assuming that these parabolic relationships hold over the entire acceleration run. In which case, so here I'm going to say we assume we're going to assume that the thrust is parabolic in v over entire acceleration. And if we do that, then we can now write that the acceleration distance is w over g from 0 to v LO. This is v liftoff. V minus VHW divided by, again, our coefficient, which I'm not going to work on here. It ends up getting kind of hairy. That's why I'm not including those coefficients here. But I invite you, if you're interested, to go ahead and add them up and figure out what those coefficients are. Times some coefficient times v squared times dv. Okay? And here then we can integrate this and get, integrate. Wow, sorry, that's really ugly. So we can integrate that and get our acceleration distance. Now if we make one more assumption and assume that net force doesn't change very much with velocity, so nearly constant, in v, then this gets even simpler. Okay, we can actually perform the integral and we come up with an approximation. There's one more assumption here. We also are assuming no wind. That's kind of important. Okay, so assuming the net force is nearly constant in v and there's no wind, then the acceleration distance can be approximated as w times v LO, which is the liftoff speed squared, divided by 2g t minus d minus fr. So that's an approximation. Now the liftoff speed, let's talk about that for just a second here before we finish. So the liftoff speed is actually dictated by the stall speed. So by FAR regulations, FAR is, I believe it's Federal Aviation Regulations, something like that. So by FAR, FAR, the liftoff speed must be greater than or equal to 1.1 times the stall speed. And if you'll recall, v stall is going to be square root of 2 over CL max times the square root of W over SW divided by rho. Okay, so in that case, then V liftoff is going to be 1.1 times all that. So if we plug this in up here and simplify, we can obtain a first cut estimate, with some assumptions made here, for the acceleration distance. And that's going to be 1.21 W squared divided by rho GSW times CL max times T minus D minus FR, where each of these forces is evaluated at about 0.7 times the liftoff speed. Okay, so this is important to make this an okay assumption, this evaluation here. So we get this little assumption. Now, just as a reminder, we did this by first assuming that the thrust is parabolic with respect to velocity, that the friction force and that the drag are parabolic with respect to velocity. And then using that assumption, we came out with a nicer expression. And then we assumed that that parabolic assumption for thrust, drag, and friction holds over the entire acceleration run. Now for drag and friction, that should be the case always, but because the lift coefficient is constant. But for thrust, we have to make that assumption, and it is a decent assumption for most power plants. But if you really want an accurate solution, you'd have to discretize it up. Anyway, making that assumption, then assuming that the net force is nearly constant in velocity and that there's no wind, we get this approximation for the acceleration distance.